class, today we're going to continue on and we're going to look at the ideal gas equation and look at other ways that we can actually use that equation for other things or solve for other things. So as an introduction, let's remind ourselves that the ideal gas law is PV equals nRT, where R is equal to 0.08206. In this section, we're going to learn how to define the relationship between density of a gas and its molar mass, calculate density, and then calculate molar mass of a gas. Now this slide I have right here is just some background information. You're not going to see it in your notes, so there's nothing for you guys to write down, but let's just kind of break down a few things. With our ideal gas law, PV equals nRT, and we know that density is mass divided by volume, we can actually rearrange our equation and get our number of moles divided by our volume equals pressure divided by RT. And if we know that moles times molar mass will get me my mass, we can actually multiply both sides of the equation to get our formulas that we use for density and our formulas that we use for molar mass. And so when you ask yourself, where did Mrs. Grove get these equations? It's from rearranging these equations and substituting in things that we know. So our density, we need to remember that is mass divided by unit volume. Our mass is measured in grams and our volume is measured in liters. So when we're looking at density, density is going to have the unit of grams per liter in our case. Now the rearranged equation that I do expect you to know is density equals P, which P stands for pressure, molar mass divided by R times T. So that weird looking M that we see in this equation, that capital, stands for molar mass, which we measure in grams per mole. So if you know the molar mass, the pressure, and the temperature, you can find density. Now, because we are working with the R constant, we do have to make sure everything is in the correct units that it's supposed to be. So I did leave a little space in your notes to write down the units that we need to know. D, which is density, is going to be equal to grams per liter. P stands for pressure, and pressure is always measured in ATM or atmospheres. Our capital M is molar mass, and that's going to be measured in grams per mole. Our R constant is always going to be equal to 0.08206, and then our temperature is always going to be located in kelvins. Now, density of a gas depends on its pressure, molar mass, and temperature. So if you change any of those things, it's going to affect the density that we see. For example, the higher the molar mass and pressure something is, the denser the gas is going to be. And both of those are actually directly proportional. So we see a direct relationship with these things. And all that means is the higher the molar mass, the denser the gas, or the higher the pressure, the denser the gas. On the other hand, temperature and density has an inverse relationship. Typically, we see the higher the temperature, the less dense that gas is. So again, we say that's an inverse proportion or inverse relationship. So when we have equal molar masses of two gases at the same pressure, but the temperatures are different, we're going to notice that the hotter gas is going to be less dense than the cooler one. And this explains why hot air balloons rise up and why we see certain weather patterns. If you've ever noticed in a house that the bedrooms that are higher up or upstairs bedrooms tend to be hotter than the downstairs bedrooms in the summer. So here we have a question looking at this relationship, and it says which gas is the most dense if they all have a pressure of 1 atm and they're all at the temperature of 298 Kelvin. So since all of these gases are at the same pressure and the same temperature, what we're going to be looking at is the molar mass. So you need to find the molar mass of each one of these gases. If you look at CO2 and calculate its molar mass, it's going to be 44.009 grams per mole. N2O's molar mass is actually going to be about 44.013 grams per mole. And then chlorine, or Cl2, is going to be 70.906 grams per mole. So here, if we're looking at this, which one's going to be most dense? It's going to be Cl2. And then if we need to explain it, our explanation, it's because it has the highest molar mass. Remember, mass and density are directly related. So the most dense is going to have the highest molar mass. Now on your notes, you're going to notice there's one that's set right under this example that says homework. That is for you guys to do as homework that we'll go over tomorrow. We're going to skip that and go to the problem that says calculating gas density. And so here it's going to say, what is the density of carbon tetrachloride vapor at 714 torr at 125 degrees Celsius? So we need to look at our equation. And so our equation for density is density equals pressure times molar mass divided by your R and then T. We have to make sure that everything is in our correct units. So right now our pressure is in torr, but we need it to be in ATM. So to get from torr into ATM, we're actually going to take 714 divided by 760 in order to get that into our ATMs. When we do that, we get about 0.9394736,842. Then we're going to look at our temperature. Our temperature right now is in Celsius, but we need to get it into Kelvin. So we're going to actually add 273.15. When we do that, our temperature actually comes out to be 398.15 Kelvin. The last thing that we need is our molar mass, and that's going to be based off our formula. So it says we have carbon tetrachloride, which is actually 1 carbon, 4 chlorine. And so we just have to find the molar mass of this, which we end up getting as 153.823 grams per mole. From there, we have all of the information in order to plug it into our equation. So we have our pressure, 0.9394736,842, times our molar mass, 153.823, divided by our R constant, which is 0.08206, multiplied by our temperature, 398.15. Whenever you're plugging this into your calculator, make sure you plug in the top part, you equal it, you plug in the bottom part, equal it, and then divide those two numbers. So make sure you guys are dividing correctly. You get about 4.23109223, but we want to make sure we have the correct number of sig figs, and based on our numbers in our problem, it should be 4 sig figs, which is 4.23. Since we're asked to find density, we want to make sure to use proper units. So density will be grams divided by liters because it's going to be our mass divided by our volume in order to get that. Let's look at this other practice problem. It says the mean molar mass of an atmosphere of the surface of Titan, Saturn's largest moon, is 28.6 grams per mole. The surface temperature is 95 Kelvin and the pressure is 1.6 atm. Assuming ideal behavior, we're going to calculate that density. So I'm going to put up here the equation again. Now we're going to make sure everything is in the correct units, and actually everything is. Our temperature is in Kelvin, our pressure is in atm, so we have everything in our correct units. We can just plug and chug here. So our pressure is actually 1.6. Here our molar mass, and our problem tells me it's 28.6. Our R constant remains the same. And then our temperature in Kelvin is 95. Again, you want to make sure you multiply the top, multiply the bottom, and then divide those in your separate steps, and you get about 5.869902639. We want to round to correct number of sig figs. In this problem, because of the 1.6 and 95 having the lowest number of just having 2, we're going to actually round this to 5.9. Again, we want to give it a unit, and since it's density, it's grams per liter. You have 2 homework problems, and so those are what you guys are going to be doing for homework instead of given a sheet. So once you guys do those, we'll go over them tomorrow. Now we're going to look at calculating molar mass. We can actually rearrange that equation to solve for molar mass as well instead of density. And our equation is molar mass equals density times your R constant times temperature divided by P. So don't forget that your molar mass must be in grams per mole. Density is grams per liter. Your R constant is always 0.08206. Temperature is always in Kelvin, and pressure is always in ATM. So our first example is through experimental measurements, the density of a gas was found to be 3.09 grams per liter, and the gas of an unknown molar mass was at a pressure of 735 torrs at 31 degrees Celsius. So I'm going to put up here our equation. So molar mass equals dRT divided by P. We must make sure everything is in correct units, and right now we have things that are not. So for example, our pressure is in torr, but we want to get that into ATM. So we're going to actually take that 735 torr and divide it by 760 in order to get it into our ATM, which we get about 0.967105262. We also need to get our temperature into Kelvin, so what we're going to do is we're going to add that 273.15 in order to see that our temperature should be 304.15. Our density is already in the correct units, so now that everything is switched to the correct units, we're just going to do our old plug and chug, where our molar mass, or X, equals density, which is 3.09, times our R, 0.08206, times our temperature, all divided by our pressure. Just like all the last problems, we're going to multiply across the top, equal that out, and then divide by our bottom. When you end up doing that, you get about 79.7451184. Rounding to the correct number of sig figs, it should be 3 based on our values in our sheet, so this is actually going to be 79.7. Now we have to do a unit. Because it's asking for molar mass, molar mass is always going to be grams per mole. And our last problem is calculate the average molar mass of dry air if it has a density of 1.17 grams per liter at 21 degrees Celsius at 740 torr. Again, same equation, but we have to make sure everything is in our correct values. So here, to get our Celsius into Kelvin, still add 273.15 to get 294.15. Our torr needs to be an ATM, so we're going to divide that by 760, and that actually ends up getting me 0.973684210.5. Our density is already in the correct units, so now that everything's in our correct units, we can go ahead and plug and chug. So our molar mass is X, our density is 1.17, our R value is always going to be the same, our temperature 294.15, all divided by our pressure. When we actually solve that out, you get about 29.00468142. And then looking back at our numbers, we're going to have 3 sig figs, so this actually rounds to be 29.0 grams per mole. Again, you have 2 homework problems that you guys are in charge of. We will go over those answers, so try your best. And that is the end of today's lesson. If you guys have any questions, please let me know. Have a great day.